So I'm going to introduce the final speaker of the conference, or seminar, Jeffery Griffith, who is one of the most distinguished probabilists from Great Britain. He's particularly well known for his research and books in percolation theory and other related models. And he's going to tell us why delta, or why nabla rather, or why not.
Thank you very much, Russ. Don't know whether I can live up to the introduction. So this lecture title is an entry for the competition for the shortest lecture title. Of course, anybody can make the lecture title shorter, but of course you have to balance content with content, if you see what I mean. And so this seems to me to be almost minimal. This lecture title also was partly derived from a conversation with Ander Holroyd yesterday. You can perhaps work out what the change might have been, given that I tell you there was one change, and it was not the deletion of the hyphen. Actually, there were two changes. One was the deletion of the hyphen, in the interest of brevity. And as Russ says, why nabla? Or why grad? So the question is partly answered by this gentleman. So this gentleman is, this is a photograph of Arthur Kennelly. Arthur Kennelly was born in 1861 and died in 1939. Arthur Kennelly was fortunately a member of the National Academy, and so when he died, an obituary was published. The obituary contained his photograph, and the first paragraph of the obituary, so we were talking about obituaries the other day over lunch, the first paragraph of his obituary, I think, well, I don't know whether we would want such a paragraph or whether we would not want such a paragraph, but it's a very powerful paragraph. Maybe it's typical of the time, of obituaries of the time. To few and only to the few has been granted the inestimable privilege of active and close participation in almost the entire range of development of such an enormous and such a useful field as that of electrical engineering, comma, from the pioneer days of the telegraph and submarine cable through the earliest stages of practical application of the storage battery, the electric light and the telephone, and on to the flowering of the art as represented by the present status of electric power generation, transmission and utilization, and of electrical communication. And to few only has there been granted the friendship, esteem, and professional respect of so many outstanding contemporaries in any art, as are represented by such names as Rowland, Elihu Thomson, Edison, Steinmetz, Sprague, Houston, and Bruijn in the United States, Heaviside, Clark, Lord Kelvin, Fleming, Jenkin, and Preece in England, Mascar, Blondel, and Ferrier in France, von Helmholtz in Germany, Marconi and Giorgi in Italy, Nagaoka in Japan, and many others throughout the world. But to Arthur Edwin Kennelly was granted both the privilege of such a participation in an art and such a friendship and esteem from the principal joint authors of its development. With his death on June the 18th, 1939, Harvard University and the Massachusetts Institute of Technology lost a deeply respected professor emeritus of electrical engineering. The profession lost one of its early pioneers and most striking figures, and the National Academy of Sciences lost a distinguished and valued member. So what can I tell you about Arthur Kennelly is from the point of view of this talk, is that he discovered the star delta, the star triangle transformation for electrical networks, or as physicists mostly put it, the Y delta transformation for electrical networks, or as we have just recoined it, the Y nabla transformation for electrical networks. The obituary actually continues, in my regard, to be a slightly disappointing obituary. It's purely scientific and it's purely laudatory. It has no criticisms. I hope when I die somebody will write an obituary and it will have criticisms. And furthermore, so far as I can tell, Kennelly was entirely a man of his art. That's to say, no women are mentioned, no children are mentioned, no activities are mentioned. So, so his life as a scientist was obviously very esteemed, and all we know about him through this obituary is his life as a scientist. I think obituaries, as you see, as dress, had he given this lecture 100 years ago, he would have been very much better dressed than me. Things have changed. So anyway, here is the Y nabla transformation for electrical networks, very well known. Take a triangle somewhere in a network. You've got this big network, and you've got these three edges, these three resistors that form a triangle, and they have resistances. And if you replace the triangle by the star, and you choose the resistances of the three red edges appropriately by that formula, then what happens? Nobody notices the difference. Okay. So by nobody notices the difference, at least we can say the following. In the mother network, remember there are a whole load of other connections and potential differences and applied PDs and so on. There are the same resistances between pairs. The same currents will flow and the same energy will be dissipated. So nobody notices when you make this change. Of course, there are two other changes which are very well known, the series and the parallel transformations. They're not part of this lecture, though of course they're very useful techniques. And this result is in the paper referred to at the bottom. It's very difficult to get hold of this paper. Undoubtedly, you can get it in the older, the universities, the archives of universities which have been around a long time in the United States. You can't get it in Cambridge University. Google has very recently, when I first looked on the web for it, there was no track of it. There was the occasional volume from around 1900 which had gone onto the web, find its way onto the web, but not this one. Google has now scanned all the years around 1899, but unfortunately the volumes for 1899 are only available in snippet form. So I think that means you have to pay to get the full version. Whereas 1898 and 1900 are available in full form. So maybe they know, somebody at Google knows this result and thinks they can make money out of it. It's probably made a great deal of money already. So this star delta transformation is a little thing. But this little thing turns out to have tremendously far-reaching consequences for a whole variety of problems in our art, that's to say probability and statistical physics. So starting from something which is very small, what I want to show you is how it develops, and much of that is familiar to us anyway, the star triangle transformations for other systems, and then show you a recent application to percolation, and it's very convenient that Jeff has introduced percolation for you, so I don't have to do that. I wasn't intending to do it anyway, but you might find it nice that Jeff's already talked about it. And in this lecture, there are almost no equations beyond equations at that level. This is a lecture by picture, and there is another lecture, which is a lecture by equation, which I've never actually given, which would be longer and by definition more complex. So spin systems, Ising models, Potts models, that sort of stuff, Heisenberg models. There are also Y-delta star triangle transformations for these guys. So in these guys, the vertices are allocated spin variables. In Ising model, it's plus or minus. Potts model, it's some integer between 1 and q, and so on. These spins interact along edges, and there's a strength of interaction, which is a function of the edge. So in general, different edges have different strengths of interaction. There's the j's. So you have some model. So a model amounts to, in statistical mechanics, as writing down a partition function. So you have these spins, you have these interactions, you write down the energy of any configuration, call that E. You write down e to the minus beta times e, that's the Gibbs formula, that's the weight of the probability distribution. You sum that over all spin configurations, that's the partition function. So the partition function is an object, a function which is defined in terms of sums over spin configurations, and it's the summand is something which depends upon the j's. The j's determine the individual energies of interactions. So the general form of the star triangle transformation, which is sometimes valid and sometimes not, it depends upon the system, and depending on the system there may or may not be some formula of this sort here that makes it work, is if you take a star and you replace it by a triangle and replace it by a star, you have to stand on your head to see the Y nabla in this one. So I suppose I should redraw all my pictures again. And then there is sometimes some function which tells you how the k's are given in terms of the j's. Actually, this f shouldn't depend upon I here. Okay, you see on cyclic permutations and so on. So yes, let's leave it as it is. So some function which tells you the k's in terms of the j's, such that if you make this substitution, then what happens? So in statistical mechanics, what happens is that the partition function is unchanged. So when you sum over all configurations, you're now summing over a slightly different family of configurations, so the summands are different, but when you do the sum, you get the same thing, or at least it's not usually the same thing. It's usually changed by some multiplicative constant, and then you've put that into the normalization, so you renormalize by that multiplicative constant so that the partition function is unchanged. And this lack of change of the partition function is an indicator to statistical physicists that something is going on, and then you can do the statistical physics that follows from this to understand something about the process. And this was known for the Ising model to Onsager, apparently, but though Onsager didn't lecture on the subject until into the 70s, and it was used by Vanier in an early review of the Ising model. probably, I would guess, in the 40s. It's well known that such functions f exist for Potts models and for something called the chiral Potts model, and there are various other classical quantum models for which such functions can be constructed. It's not universally the case that whatever model you write down, you can find these things, but you sit down and you play with things for a given system to try to find a star triangle transformation, and then you try to use it. And the name that is most associated with using this construction in physics is Rodney Baxter, who, with his co-authors in the late 70s and in the 80s, made tremendous progress understanding the structure of statistical physical models in the presence of a star triangle transformation. Such was their success, and also the earlier observation actually of Yang, that the star triangle transformation is useful, that physicists commonly call this the Yang-Baxter equation. Now, to little me, there's some difficulty talking about the Yang-Baxter equation. It's the usual problem. We have to understand what it means. And of course, it doesn't just mean an equation. Well, it probably could be distilled to an equation. It means a construct. It means a vision. And so you try to find out what it means. So you might think that if you read the Encyclopedia of Mathematical Physics, you're going to learn what it means. And actually, the essay there by Perk and Yang is not bad. But Wikipedia really, in my opinion, takes the biscuit. I don't know who wrote this. Is the author of this Wikipedia page in the room? I doubt it. So starts off pretty well. This is the introduction. This is the blurb at the top that's supposed to, that the bus conductors can understand. And it says the Yang-Baxter equation is an equation which was first introduced la-di-da. Yang-Baxter refers to a principle in integral systems, taking the form of local equivalence transformations that appear in a variety of contexts. And you think, well, electric networks, that sounds pretty good. Knot theory, I know about that. Spin systems, I'll be able to understand this article. And then it moves on to the next line and accelerates into hyperspace. And somehow, there's I'm somewhere here, I guess. And so this is, there's something, one learns something a little bit about Wikipedia here. But this is, by Wikipedia standards, this is probably a pretty good article for experts. But if you want to, as a result of this lecture or not, you might want to think about whether the Wikipedia article is the right way of phrasing this. Because for us, the Yang-Baxter equation is this massive, it's a construct. It involves algebraic formulations, and it's a very interesting object, a very interesting vision in pure mathematics, as well as its applications in statistical physics. But for us, it's really just the star triangle transformation, right? So these generalizations for percolation, even for the Ising model, it's useful to see the associated algebra and geometry in a certain way that I will show you, not the algebra, but the geometry. But beyond that, we don't really need to know about unital associative algebras for the purpose of this talk. So star triangle for percolation. So Jeff's talked about site percolation. Remember, each site is either black or white. Bond percolation, so each site is either sort of there or not there, two states for each site, independence between sites. Bond percolation, you do the same for the bonds, not the sites. So each bond is either present or absent. Each bond is either present or absent with a certain probability, independently of all the other bonds. So some bonds are present, some bonds are absent, and you ask the question, what is the probability that there's a very large connected cluster of bonds? The bonds form a subgraph. What is the chance of a very large cluster in that subgraph? If the graph is a lattice, then you might ask, what's the probability of an infinite subgraph formed by the connected bonds? The bonds which remain present. So a bond is present with a certain probability, and these are the probabilities associated with these three bonds. And if we replace this triangle by this star, and the right probabilities to use over here are these probabilities. So P1 here becomes 1 minus P1 on the corresponding edge here. And then you ask, is this enough? And the answer is no. You also need this 3 vector to satisfy the equation that kappa is 0, where kappa is this function. Okay? And that's essentially if and only if. I guess it is if and only if. So essentially is one of those weasel words, isn't it, in mathematics? That's like generally, that means always, if not always, but not always, if you see what I mean. I like what's the best? It's generally I like, which means that it's true always, and except when it's false. So whenever the p's satisfy this formula, So whenever the p's are replaced, satisfy this formula, then when you replace the p's by 1 minus the p's in the natural way, then all the usual things happen. The local connectivity has got the same law. Remember, the triangle is sitting in some other graph, and you're interested in what's the probability 2 vertices are connected, or 3 vertices are connected and the fourth isn't. Then when you make this change, and those vertices are off this picture, in fact they can even include, of course, the vertices of the triangle, you have to be a little bit careful because you're introducing a new vertex in this transformation, and you have to keep track of that in the later part of this lecture. Then those connection probabilities are unchanged by this transformation. I think it was probably observed first by Sykes and Essam when they wrote down the critical function, the critical probability for the bond percolation on triangular and hexagonal lattice, but it might go earlier than that. And what you notice is that it only works under this assumption. So far, there's nothing here about criticality. This is just a certain, you can work this out in 10 minutes. It's a 10-minute computation just to check that this is correct. But there is the implication from talking about Yang-Baxter for statistical mechanics that star triangle in some sense tells you information about critical points. And so it is the case, actually, that if you take the star triangle transformation on one of these graphs, for example, what am I saying? Take the triangular lattice here, that's the triangular blue lattice, then it's got and think about P as a constant for the moment, each Pi is the same. Then there's a critical intensity for bond percolation, and that critical intensity is given exactly by kappa of PPP, when all the P's are the same, equals 0. So the validity of the star triangle transformation in some sense characterizes the critical point of the triangular lattice, which is formed of many of these triangles. So there is an interplay between critical points, critical surfaces, and the validity of the star triangle transformation.
So, quick question. So for spin systems...
I hope you're not going to do to me what you did to Asaf. Have you still got a question?
For spin systems, you didn't need any equivalent of this condition in ret, right?
I didn't write that down, if you're careful. I didn't say it. I didn't answer that question. Is that a question or a statement?
Yeah.
I didn't hear the question mark. Sorry.
Does it work for spin systems? It works for any...
Well,
it's
slightly complex. It's a very good question, Ander, and let me just come back to it later because I'll probably talk about that in a minute in the context of random cluster models. But it is absolutely a very good question, and it's something which I think has been... Well, maybe some people have explored it sufficiently, but I haven't explored that sufficiently. I think there is more to be said about that. I mean, we understand the answer to the question, but the answer is sometimes yes and sometimes no, and I haven't really understood why yes and why no. I mean, you can see technically why yes and why no, but you can't really, haven't understood the implications of that. So one thing now is that, of course, this is just replacing one probability by another, and the laws are the same. But of course, what we do in probability is, so the laws are the same. It's much more just than the partition function. The partition function being the same, you have to do a lot more work to extract information from this. But these laws are the same. It's a much higher dimensional object. And furthermore, a useful thing to do is not to do this sort of analytically, but to do it via coupling. So what you really want to do is have a configuration on this guy and replace that by a configuration on this guy, such that the pair jointly has this property of invariance. So there is a coupling of the star triangle transformation. It's very natural. It's very obvious what you do. And that coupling is very useful for what's going to happen next. That's what makes this work, the work I'm going to tell you about, intrinsically probabilistic rather than statistical mechanics. So this is just a reminder that graphs in 2 dimensions have duals. The square lattice is self-dual. The triangular lattice is dual to the hexagonal lattice. And of course, the triangular lattice has the property that if I change every other triangle into a star, that also changes the triangular lattice into the hexagonal lattice. So there are 2 ways of getting from triangular to hexagonal, and so you get an equation. Those 2 ways give you an equation, and those equations tell you exactly that the critical surface of the triangular lattice is kappa of, this should be non-bolded, this should be when all the p's are the same. It's not the vector p, all the p's are the same. It is exactly given by kappa p equals 0. Okay. Now, random cluster models, this is partly in a response to Anders' question. Just mention this, I think it's probably 2 transparencies, no more, and we're not going to come back to it until the very end. This is percolation, so you have a graph, you have an edge E. An edge E is either open or closed, black, white, 0, 1, whatever you like. So, and so a configuration is a configuration omega where each edge gets a 0 sitting on it or a 1 sitting on it. So, reminiscent of Jeff's lecture. So if Q weren't there, this would be P to the number of open edges, 1 minus P to the number of closed edges, so that's percolation. Now we muck it up by putting in this Radon-Nikodym derivative Q. Q is not 1 minus P necessarily. Q to the K of omega, where K of omega is the number of open clusters. So you look at a graph, you take a configuration, throw away the other edges. That graph has a certain number of components, including the singletons. Count the number of components, call it K, put that up there. And then you end up with another measure. This is a very interesting measure. It's an interesting measure because, as it was noticed by Fortuyn and Castellane, that it corresponds to the Q-state Potts model when Q is a positive integer. So Q equals 1 is percolation. Q equals 2 corresponds in a certain interesting, slightly geometric way to the Ising model, to the two-state Potts model. Q equals 3, 4, 5 correspond to the Q-state Potts model. So this is a kind of a geometrical representation of Potts models in which connections correspond to correlations. So it's a good place to explore the geometry of the Potts model. Now this has a Y delta star triangle transformation. And actually, it's written down explicitly here. So each edge in this picture has got in this formula has got a parameter p, but p could depend upon the edge. So expand the generality of this. So each p. So this is the product over all open edges pe of pe, where pe is the parameter of the edge. Then the right way of parameterizing this model is you take the edge parameter p and you take p over 1 minus p and call that y. You can see y because you've got a 1 minus p to the minus omega there. That's why that happens. And then the capital Y's have to be given in terms of the little y's by this formula. And you require a certain function of this vector of y's to be 0, where this is the function. So this looks a little bit like the triangular lattice. Critical point is not quite the same because my p's have become p's over 1 minus p's, and my q equals 1 has become a general q. So there is a y delta transformation here under this assumption. But Anders' question is a very interesting one. Here we notice that this is also the critical surface. So in the situation where all the y's are constant, this is the critical surface of the so we take all y's constant, look at the triangular lattice. So tile the plane in the natural way with these triangles, copies of these triangles, these equilateral triangles. Then there's a constant y, so there is a critical point of the random cluster model, and the Beffara-Duminil-Copin theorem says for triangular lattice that is the critical point. This gives the corresponding cubic in y, gives you exactly the critical point. So we strongly believe that if you tile the plane with these triangles, but you retain y1, y2, y3, this generalized vector of parameters, then this gives you the critical surface of that two-dimensional random cluster model, but we don't know how to do that. So the Beffara-Duminil-Copin theorem really seems to need all the y's to be equal, and we don't know how to get away from all y's being equal. In fact, one of the reasons that we started this work was to try to answer that question, but we haven't yet succeeded. Now, in particular, this works for the Q-state Potts models. If Q just had to be a real number, a positive real, well, bigger than or equal to 1 if you want the FKG inequality, so you want all the paraphernalia that predicts critical points. But Q could be an integer. And if Q is an integer, this is in some sense related to the Q-state Potts model. And the Q-state Potts model, I've already told you, has a star triangle transformation, or by implication here. But the funny thing is that the Q-state Potts model has a star triangle transformation whenever Q is not 2. But when Q is when Q is not 2, it works at the critical point. When Q is not 2, it works for all temperatures. So there's some magic about working in Z2, as it were, Z sub 2, which gives you a star triangle transformation for all parameter values. But when you work away from, when you take Q bigger, then you need to work at the critical surface. You have some extra equation. And so this is even stranger in the context of the random cluster model. So the random cluster model with Q equals 2 has a star triangle transformation only when this equation holds, when this equation is equal to 0. On the other hand, it's a geometrical representation of the Ising model, which has a star triangle transformation for all temperatures, and that is to say there is no such equation. And this, I think, has not been, well, it may be fully understood by some, but its implications are not grasp. I mean, it's some sort of algebraic property of the sets that you're working over. It's not difficult to see why this is true. What I don't fully understand somehow is why it's true. Okay. Now for something completely different. This is a rhombic tiling of the plane. In this picture, there are many different types of rhombi. All my rhombi are going to have side length 1. So, of course, when you rescale, I can make the side length what I want. So I'm going to refer to 1 as the length of a rhombus, length of the side of a rhombus. So this is a rhombic tiling of the plane. And what I'm asking you to accept, and actually I very much doubt if it can, be extended to the whole of R2. So this, but just accept the moment. This is an image of a bit of a rhombic tiling of the plane. And rhombic tilings have very beautiful structure. One very famous theorem about rhombic tilings is the theorem of Penrose. One gets so confused about these Penroses. This is Roger Penrose, who established the existence of a rhombic tiling of the plane which is aperiodic. So a rhombic tiling uses only 2 types of rhombi, such that there is no rotation or translation of the plane which conserves the tiling. So there's a very famous tiling. It's in fact an example of a whole family, a whole continuum of tilings. And so his paper, which was what you might call a popular paper, was followed by 3 very serious papers of Bruijn in the early 80s, published in the Proceedings of the Royal Dutch Academy. They're very, very beautiful papers that show the connections, how to generate sort of generalized Penrose tilings, and how to show connections between 2-dimensional tilings and slices through 5-dimensional cell systems, and a variety of other rather beautiful things, one of which I'm going to show you in a moment. So think about this for the moment as something completely different, unless you know the connection. Well, even if you know the connection, but you see the connection soon between this and the star triangle transformation. So these are rhombic tilings. So rhombic tiling of the plane doesn't have to be aperiodic, it's just a rhombic tiling of the plane. Now, from the rhombic tiling of the plane, there are 2 graphs you can construct, and it's a dual pair of graphs. So the first thing is you notice that this rhombic tiling is bipartite. Every rhombic tiling is bipartite because every cycle has length 4, because every cycle is a union modulo 2 of the quadrilaterals that form the rhombic tiling, right? So every cycle is length 2, so it's bipartite, so we can color the vertices red and white in such a way that every edge joins a white vertex to a red vertex. Did I say vertex or edge? Anyway, there we are. Now what I'm going to do is join up the red vertices across diagonals. When I do that, I get this red graph. That red graph has a property of isoradiality. This is a word, I believe, coined by Kenyon. So this red graph, concentrate on the red graph, this is an isoradial graph in the sense that if you take any face of this graph, it has a circumcircle, which passes through all the vertices, of constant radius. Radius 1 in this case. Proof? Well, look, this vertex in the middle is not in the graph, but it's distance 1 from each of the vertices. So if I draw a unit circle sent to this vertex, it is the circumcircle of the triangle, and since this is true for all these faces, every face here it has a circumcircle of exactly the same radius, and therefore it qualifies for the name isoradial graph. So isoradial graphs were first introduced in 1968 by Duffin in a very simple but beautiful paper. Duffin showed the relationship between rhombic tilings and isoradial graphs and discrete holomorphic functions. So he asked for a theory of, holomorphic is a function of a complex variable, it has certain properties. How could we discretize this? What is the right way of defining a function on the vertices of a graph, which has some property of reminiscent, closely related to that of the analytic functions, and this led Duffin to consider rhombic tilings and isoradial graphs, because isoradial graphs somehow are the right places, or rhombic tilings actually are somehow the right places on which to have these discretely holomorphic functions. So very nice paper, very easy to read. Now, of course, I could have joined the white vertices instead of the red vertices. And had I done that, I'd have obtained a pair of isoradial graphs which are dual. One is dual to the other, each is dual to the other. Right? So duality, we know in probability, 2-dimensional probability in physics is a very useful concept. This is how duality arises in rhombic tilings. One more thing that Bruijn pointed out, which turns out to be extremely beautiful and useful, is there's something else you can do on a rhombic tiling. You can drive a train across it, a railway train. And what you do is you come up with your railway train here. This is one track. This is one rail. This is the other rail. And you drive your railway engine across here with your left rail and your right rail. And when you get to this edge, you have to turn a corner to make that your left edge and your right edge. And so your wheels traverse these tracks. And you end up driving your train along this blue line here. So whenever you cross from one rhombus, you're driving across the middle of a rhombus. Whenever you get to the opposite face, you just reorient your direction to the next rhombus. You carry on in that way, and that gives you a blue track. And of course, each rhombus is the meeting of two train tracks. So across each rhombus, there are two train tracks. You can make the map of train tracks. And there are 3 of the train tracks. These train tracks are just the way, or a very nice way of encoding rhombic tilings. Any rhombic tiling has got a set of train tracks. It's convenient to think of train tracks in every possible way. I mean, first of all, as just being joining the midpoints, straight line segments joining the midpoints, or being the actual sequence of rhombi that you traverse as the train moves across it, or alternatively, just extract the blue graph and allow yourself any homeomorphic image of that blue graph, so you don't create any crossings, just think about it as a graph. And so you can ask about the graph of train tracks. So we call these tracks. Bruijn called them ribbons. Some people call them train tracks, and there is other notation around. But these train tracks are really neat things. So let me just summarize this very briefly. Rhombic tiling generates an isoradial graph, in fact, 2 isoradial graphs which have the primal dual property, and in addition, they generate families of train tracks. Now, train tracks, so rhombic tilings give you train tracks. Rhombic tilings are pretty difficult things to draw. Well, aspers are not difficult to draw, but you want to set off. You only know your rhombic tiling. It's a big object, and so it's quite worthwhile sometimes to be able to draw them via train tracks. So, what are the characteristics of train tracks? So, train tracks. This is at the bottom here. Bruijn pointed out that no track intersects itself. You see, each track crosses a rhombus side, and all the sides it crosses have got the same angle, because that's the definition of a rhombus. And so because of that property, you can't self-intersect, because you carry on round, you're going to get something nasty is going to happen when you cross, and that can't happen. 2 train tracks can cross, of course, they cross on rhombi, but they can't cross twice, because once again, you'd be contradicting the conservation of angle. So Bruijn pointed out that those are 2 properties of train tracks, and Kenyon and Schlenker proved that those are actually necessary and sufficient to generate a set of train tracks which comes from a rhombic tiling. So those are 2 interesting properties of train tracks. Now, so if you write down descriptions of examples of train tracks, there are 2 examples of a set of train tracks. Now, I don't want you to think of train tracks as being a rigid embedding of a graph in a plane. I just want you to think about it as a graph. So you can move it around a bit. I just don't want to create any extra intersections. So this is a set of train tracks of the square lattice. The square lattice is always generates itself. You take the dual, it's still a square lattice. A set of train tracks is still a square lattice. It's very hard to get away from the square lattice. Actually, the square lattice of which this is the set of train tracks is the usual square lattice. It's the horizontal vertical one. It's just the train tracks give you some angles. They go to funny angles. Just draw it. It's easy to see. But instead of taking 2 of these sets of parallel lines, if I take 5 of these sets of parallel lines, and I adjust them a little bit, I move them around a little bit so that you only get pairwise intersections. You don't get any 3-ways or 4-ways or 5-ways intersections. Then this is a set of train tracks, and it's a set of train tracks of a generalized Penrose tiling. An example of that, here is a Penrose tiling whipped from the web, bit of the Penrose tiling, the original. Here is the isoradial graph that generates. There is the isoradial graph, there is a set of train tracks, and there you see, according to the colors, you see exactly the 5 sets of colored, not parallel, but non-meeting, doubly infinite, non-intersecting lines of constant color that constitute the train tracks of a Penrose tiling. Now, what's this got to do with percolation? So a variety of people have worked on systems of this sort, certainly Baxter and his successors and his collaborators, but not in the context, I think, of Penrose, in a related sort of more combinatorial context, but without explicitly realizing or understanding, or at least expressing their understanding that what they were doing was connected to isoradiographs or rhombic tilings. So probably, I guess, Rick Kenyon and co-authors, certainly Rick, were the people to write down explicitly the correspondence between these rhombic tilings, isoradial graphs, and the models of statistical physics. This is percolation. So we're going to do percolation on an isoradial graph. So the gray circles are the circles that demonstrate this is an isoradial graph. Underlying this, there's a rhombic tiling. So we've got this graph here, this red graph, and I want to tell you what the right p's are. So here's an edge. That edge has two faces abutting it. Those two faces have circumcircles. Those circumcircles have centers. Because these are isoradial, all these black lines have got radius 1, and so this is another rhombus, and so these angles are equal. So call that angle theta. So P, for that edge, the parameter of bond percolation, is given by this formula. That's the right formula. If you wanted to do the Ising model, then there'd be a different formula for JE in terms of the angle theta. If you want to do the random cluster model, there's another formula. In fact, there's a general formula which has got a Q in it. For percolation, that is the right formula. Let me show you why it's the right formula. Well, we're now going to go back to, one thing you notice about this is that if you go to the dual graph, so let's just establish some notation. An isoradial graph G, each edge has got a certain probability of being open called P. I'm going to call that measure P sub G. So there's a canonical measure P sub G on an isoradial graph. If you go to the dual graph, the dual isoradial graph corresponds to flipping this. P of E over 1 minus P becomes 1 minus P over P. That's just the geometry. Theta goes to whatever it is, minus pi minus theta. And so the dual graph G star has got the isoradial measure, which also comes from the isoradial formula. So this formula preserves the natural duality relation of percolation measures. So that's one reason why it seems okay. Passes the first test. The second thing is that it gives a very harmonious explanation of the star triangle transformation. So this has been understood for some years. This is not a part of our work. Our work is to exploit this statement. So first of all, let's think what the star triangle transformation does. Here's a triangle. A triangle, now because this is an isoradial graph, each of these edges corresponds to a rhombus, so this triangle comes from 3 rhombi stuck together in that way. Now, if I fix the outside, I guess I've heard David talk about things like this. You're going to look at me in a baffled way, but I'm sure I have, David. So if I fix this external hexagon, that's the word you were missing, I think, Asaf. But you made me smile. Then the inside, there are exactly 2 rhombic tilings of the inside. There's this guy, and one is switched from the other. It's an interesting move. And if you make this move, then the isoradial graph, instead of having this triangle in it, has got the star. So this also switches the measure. So the P's here are now given by this new isoradial graph, and those P's are exactly those given by this formula. This is the formula under which this mapping is exactly the star triangle transformation percolation. So what that means is, if you have a sequence of graphs which are isoradial graphs, you can make these star triangle transformations either arithmetically or geometrically. And so the geometrical embedding of this star triangle transformation is a very useful thing to be able to do, because you can think geometrically in doing this. So you can make graph theoretic changes to your graph, and you know that the connection probabilities are going to remain the same, so long as this is the nature of the graph theoretic changes. They're basically flipping the rhombus configuration within a hexagon. Was that chit-chat or was it a question? By the way, I wanted to tell you you're a really good audience. Two reasons. You're almost all here since, and only one person has his laptop open. Okay. And it's not me, for once. Right, so now, so here's a theorem. So this is the main theorem of the lecture. And this theorem is called criticality and universality. So we have this family, we have isoradial graphs. Now, we want 2 conditions on the set of isoradial graphs. Let me just see what it says, 5:15, not much time to go. So, but did I start on time, Chair?
5 minutes late.
5 minutes late, thank you. So the 2 conditions are the square grid property and the bounded angles property. The bounded angles property says you've got these rhombi, you don't want them to be too flat. At least you don't want them to be infinitely flat. So the angles of the rhombus have to be bounded uniformly away from 0 and pi. Otherwise, you could have a lot of really flat rhombi that could accumulate somewhere, and that could be very unnatural, and it would cause trouble. with the estimates. And it might even, and in fact it changes the theorems. Do the theorems cease to be completely true in such a situation? So this condition is necessary, bounded angles property. The square grid property is that the track system of the graph contains a square grid. Now remember, the track system of Z2 was a square grid. The track system of the Penrose tiling was 5 sets of parallel lines, so it contains 5 choose 2 square grids. So I think you see what I mean by a square grid. So this we think is not necessary, but at the moment our proofs need this. But we don't regard it as a big assumption because all the graphs that you've thought about proving this theorem for have the square grid property, and a lot more.
When you say contains, you just mean there is a set of
yes.
tracks?
I mean, if you look at the track graph, then the track graph contains tracks, then there is a subset of that set of tracks which forms a square grid. That's the theorem, that's the assumption. So now the theorem is the theorem with Johan Manilescu, which says that for any G in this family, the following 3 things hold. Well, actually the first 2 things hold, and the third one shouldn't really be in the begin list. So the first thing says that these canonical measures have the box crossing property. Remember, Jeff talked about crossings of boxes. Crossings of boxes are really useful things to have because you can combine box crossings on bigger and bigger scale to form infinite clusters. And so the first says that the statement that P of G has the box crossing property basically says that the measure PG is either critical or supercritical. The statement that it's dual, because this follows, if every isoradial graph has this property, then certainly its dual has the property because its dual is preserved by, it still has these 2 conditions up there. Then the fact that dual has the boxing crossing property says that the primal is either critical or it's subcritical. And the union of the intersection of those 2 statements is critical. So you have to decide what critical means, but in some sense this generic formula for the P's, the generic P's that come from the isoradial embedding are the critical P's. So if you take one of these generic P's and if you increase every P a little bit by epsilon, or by a ratio 1 plus epsilon, you will be supercritical. If you decrease it by epsilon, you will be subcritical. Second statement is, so the second statement is that these are the critical measures. So this statement includes, of course, the square lattice. It includes a lot more than the homogeneous square lattice. It includes, of course, triangular and hexagonal. It includes just about everything you know, except those constructions of Bolobush and Riordan about self-dual graphs, which don't arise in this category. There are self-dual sort of hypergraph structures based on conjectures of Ziff and Scullard, which Baylor and Oliver have made rigorous in recent years. Those are of a different nature. But apart from that family, this includes everything you've thought of so far and a few others. And furthermore, what it shows is that what you're using, usually in proving these things, you use graph automorphisms, you use invariants under translations or rotations or reflections or something like that. But there's absolutely none of that in this. There's no graph automorphism. These isoradial graphs have generally no graph automorphisms. This works on Penrose tilings. So there's no periodicity, no rotation invariance. It's just the local invariance with respect to the star triangle transformation that makes this work. And furthermore, this set G is a universality class, to which you will say, what is a universality class? And I will say, well, it's the following. In this case, so here are some critical exponents. 1 over rho is the exponent that Jeff talked about. It's the 1-arm exponent. 1 over rho is the 1-arm exponent. Delta and eta are 2 other exponents that are present at criticality. So those are 3 exponents present at criticality. There are also the arm exponents, which are okay. The alternating arm exponents are okay, and the 1-arm exponent is okay. We can't do the 3-arm. We can't do the 4-arm non-alternating exponents, which are seem to be harder to study. But the alternating exponents and the 1-arm exponent, they are exponents, and those exponents are constant across the class script G. So statement says, but we have no theorem to say they exist anywhere in script G. So the theorem says, assuming there exists some G in this class for which, well, some subset of this set of exponents exist, I think it's enough to assume that eta exists. But I have to check this. I think you need eta and maybe the 1-arm, eta and the 4-arm exponent, I think. I can't quite remember now. But there's either 1 or 2 of the exponents in this family such that if you know that these exponents exist for any one of these graphs, such as homogeneous percolation on Z2, bond percolation on Z2, then they exist for all these graphs and they're constant across the entire family of graphs. So this is a conditional universality statement. If they ever exist, then they're constant. Now, these are only the exponents at criticality. All these exponents are at criticality. We can't do the exponents away from criticality. And the reason is because the star triangle transformation only works at criticality, and we need to make essentially a very large number, even an infinity of star triangle transformations to go from one graph to the other. Basically, we have a mechanism for taking one isoradial graph and mapping it to another isoradial graph. But in doing so, we have to perform certainly a large number, and possibly, depending on what we do, an infinity of star triangle transformations. And if you're away from the critical point, each of these star triangle transformations introduces an error, and these errors gang up on you and we can't control them. So at the moment, we don't know how to get away from criticality, but we believe this it will be true. I mean, and the alternating arm exponents, right? So, let me just remind you that these things are known for site percolation on the triangular lattice, but site percolation on the triangular lattice is not one of these graphs. Bond percolation on the triangular lattice most definitely is, but not site percolation. So we have one system for which we understand, as it was pointed out to me the other day, well, not quite, you didn't quite say this, everything, well, at least almost everything. I mean, almost everything that we asked the question to more than 5 years ago, we now understand for site percolation on the triangular lattice. But we've got this other enormous class of graphs, for which none of these theorems export, though they probably should, because we don't have SLE for these things. And yet, for this other class of graphs, we know how to identify the critical surface, and we know that it's that we have universality. So I don't have time to show you what's going on, but broadly speaking, this is an example of, you know, you've got a bit of a square lattice. That's the red graph. The red graph is a bit of a square lattice. You embed it, you add another edge to make a triangle, and that edge you can kind of propagate via a series of star triangle transformations all the way down the row. And you do this repeatedly, and this gives you an operation of swapping tracks. So remember, tracks have charismatic angles of things that they're crossing. So each track is labeled with an angle, and so this gives you a way of swapping angles. It gives you a way of moving between isoradial graphs as you swap their tracks. And it gives you a way of moving between a bit of the square lattice, which is kind of semi-regular in this sense, to a bit of the square lattice which is totally irregular by swapping tracks. There's a track across here, there's a track across here. I can swap them using this sequence of star triangle transformations, and by doing that repeatedly, I can move the bottom section up and the upper section down. You can swap, just move areas of space around. And of course, by doing it the other way, I can move this into the regular square lattice. So you can relate everything to the regular square lattice, for which you know box crossings exist at p equals a half. So so you have this mechanism of moving between graphs, and that's the oven. And in the oven, you have to put food to be cooked. And the input, the energy, is the fact that you know quite a lot about duality for Z2, self-duality. You put that in, you cook it repeatedly, and out come these theorems for isoradial graphs, or at least for isoradial square lattices, and then you have to deal with isoradial general isoradial graphs. So here is a track system, is a rather complicated track system of a general rhombic tiling, and you want to find a square lattice in it. And so what you do is, through star triangle transformations, you turn it into something that looks like a square lattice. You sort of move the tracks. You've got this square grid. You take the horizontal lines in the square grid. They're not necessarily horizontal. You kind of move them down by making these star triangle transformations, which are operations in the universe of the rhombic tiling. That gives you a bit of square grid. You've got some information about square grids, and then you release everything back, and you see what you've got. And what you've got, you have to prove two probabilistic estimates, which is actually most of the pages in the paper, which are not showing you what they are. And out of this come the theorems. Let me just conclude and also give you a summary of areas to be discussed in the future. First of all, this isoradial embedding produces critical percolation, and you have universality within this class if the exponents exist. Contrast that with site percolation, for which we know an enormous amount, but is not one of these systems. So the further directions are, I think, or obvious ones, are, first of all, star triangle transformations preserve interfaces. So understand the geometry of interfaces. Interfaces are, of course, key to SLE. So could you find a conditional exploration process? Could you show, for example, that if the exploration process converged for bond percolation on the square lattice, then it converges to SLE for all these isoradial graphs? We think that might be possible, but we don't at the moment know how to do it. Find a connection to the good guy, the guy about which we know everything. Don't know how to do that. Remove the square grid assumption, probably technical, probably a bit messy, not very appealing. We don't know how to do it, but nor do we. We feel more impelled to work on some of the other problems. Prove the universality of the near critical exponents. Again, we don't know how to do that. The only way of doing that at the moment seems to be in the Keston papers of the 80s, but the Keston papers of the 80s use, to get away from criticality, they use properties, they use automorphisms of the graph. They use some rotation invariance of the graph. Isoradial graphs don't have rotation invariance. If you assume rotation invariance as well, then somehow you're defeating the purpose of the work, which is to show that it's the isoradiality what counts rather than the automorphisms. So that's not something that we wanted to do. Nevertheless, we would obviously like to be able to move away from the critical point and understand those critical exponents. And the next thing is most of what I've said and the probabilistic estimates, which I've not told you about, are valid for the random cluster model. So why isn't there a corresponding theorem for the random cluster model? And the answer is it's the usual one, because we can't control boundary conditions. With percolation, you've got product measure. You don't have to worry about boundary conditions. They're irrelevant. For the random cluster measure, they're highly relevant because you don't have FKG. You have FKG, but you don't have independence. And so that's what we can't control at the moment. This would be very beautiful to understand how to do this for the random cluster model. Finally, I just want to remind you that isoradial graphs have featured prominently in work of Chelkak and Smirnov on the Ising model, and I guess to a lesser degree on the random cluster model. And of course they're connected because of the connection through to potential theory, through discrete analytic functions to potential theory. There's an earlier paper of Chelkak on Smirnov proving that random walk on isoradial graphs have obvious functional central limit theorems. I mean, you have to prove them, and so you have to understand why they're true, but morally the functional central limit theorem is a very natural thing to expect. And of course, by the same token, I would expect that uniform spanning tree has because of its relation to loop-erased random walk, has a very nice theory on isoradial graphs, but so far as I'm aware, that's not been explored. And that's the end of my talk. Thank you very much. I'm sorry to have overrun.